So here's our AI PyDash game. My name's Sebastian.
My name's Garrison.
My name is Ben.
My name is Victor.
All right, so introduction to our game. So our AI code is based on PyDash, which is a clone of the popular game Geometry Dash. PyDash is made by using Python and the Pygame library. The player is moved by key presses, and our idea was to create an AI that could learn how to play the game on its own. So our background, we went with the idea to use Geometry Dash, which is a popular mobile and PC game. To progress through the game, the player must jump to avoid obstacles and get to the end of each level without dying. Throughout each level, the player can change into various forms, which include a cube, a ball, and a UFO, each of which have their own unique mechanics. Geometry Dash uses one-touch gameplay, where the user must tap the screen if they're playing on a phone in order to jump, or they press a key to make the player jump if they're playing on a PC. Next slide.
So, some projects that are similar to ours is Code Noodles. A YouTuber implemented a generational learning approach in C++. A programmer on GitHub, Brainer, recorded a game on an emulator, cut the video into images, and employed a Q-learning algorithm to learn from them. While Ted and Sean of Stanford University use imitation learning and screenshots to train their AI agent. How does our project differ from the rest? In our endeavor, we employed reinforcement learning, a technique that involves an agent and an environment. In reinforcement learning, the agent interacts with the environment by performing actions that modify the current state and results in immediate rewards. Q-learning is a type of algorithm that falls under the category of reinforcement learning. Q-learning trains the agent with Q function, which is used to estimate the expected reward of taking a certain action in a given state. Q-learning that we used is called a neural network and can be used as a function approximated to estimate the Q values in Q-learning. In Q-learning, the goal is to learn the optimal Q values for each state action pair. This can be difficult to estimate directly, so we use the neural network, and it takes in the state of the environment as input and outputs, and estimates the expected rewards for each possible action. Next slide.
To delve deeper into the minutia of how our AI works, we should go over a few techniques within machine learning. There's three main types of machine learning. There's supervised learning, there's reinforcement learning, and there's another. So what we did for our project is that we had reinforcement learning, which is basically when the model trains by uh, learning what produces a better result, what produces a higher Q value. As the model learns more information, it gathers data and is able to determine the best method. And what it tries to do is obtain a better Q value as it progresses throughout the data. Now, one of the issues of this is that the Q table, which is where it stores all its data from all the inputs and outputs it has, gets too large to be reasonable for large projects, which is why we use deep learning. Deep learning simulates the human brain with layers of nodes that are supposed to interact and behave like neurons and such. There are multiple deep learning architectures: CNN, RNN, and DBN. standing for convolutional neural networks, recurrent neural networks, and deep belief neural networks. uh, the next slide.
So our project uses Q-learning, which contrasts the two different machine learning types that were used by similar projects, generational learning and imitational learning. Generational learning is a type of evolutionary algorithm that simulates natural selection to evolve solutions to problems. It works by creating a population of candidate solutions, evaluating their performance, and selecting the best ones to produce the next generation of candidates through mutation and crossover operations. Generational learning can be effective for complex optimization problems where there are many possible solutions as well as being efficient to explore the vast search spaces. However, generational learning can be computationally expensive and may require many generations to find a good solution. Imitation learning is a type of supervised learning that involves learning from examples provided by an expert. The goal of imitation learning is to learn a policy or behavior that can mimic the expert's actions or decisions in a given task. Imitation learning can be effective when there is a clear expert who could provide high quality demonstrations as well as being used to learn policies or behaviors that are difficult to program manually. Its downside, though, is that imitation learning requires access to high quality demonstration data, and it may not generalize well to new situations. Q learning, on the other hand, is a type of reinforcement learning that involves learning through trial and error. The goal is to learn a policy that maximizes the reward signal over time. Performance-wise, Q learning can be effective for decision-making problems where there is a reward signal that indicates the desired outcome. Furthermore, being able to learn complex policies that can adapt to changing environments and goals. However, computationally, Q-learning can be expensive. Q-learning requires many iterations to converge to a good policy, and it's hypersensitive to the inputs of the environment. Next slide.
So seen here are a few screenshots of our source code. The leftmost picture is our main training loop for the model. The basic structure of this loop is generating a move from the model, updating a player with that move, training our model's short-term memory with the result of that move, and adding everything about what just happened to our model's long-term memory. Afterwards, if the player died or won, the model is trained on its long-term memory, and the player's score is plotted. The picture in the top right is our getAction method. This method takes in the current state of the game and outputs a move, either generated by the model or randomly selected. As the number of games our agent has played increases, the probability of selecting a random move decreases, and the probability of the move being generated by the model increases. Occasionally, randomly selecting moves has the intended effect of exploring alternative courses of action to the moves the model would make. The picture below that is our getState function. This is the function that controls what information the agent has access to in its solving of the problem. Our agent, for instance, can see its distance to the spike that is currently the closest to it, that is on its right. The final screenshot on the far right is our reward function. This is how we define to our model if the action it took was good or bad. The actual values here are not necessarily based on anything concrete, they're just values we found that worked when we were training the model. So here's a video of our model playing on a level that we created. This is after having trained for just under 200 games. So as you can see, the agent is able to consistently clear the level at this point in its training. And here's a close-up view of the plot from the last slide. The plateaus at the top and bottom are from the player winning and the player dying on the first spike, respectively. In this instance, the model actually got stuck in a loop, dying on the first spike for about 50 attempts over here before it was able to hit some level of consistency in completing the level.
So some of these shortcomings we came across were we weren't really quite sure what to do. Some of us suggested to do like a anti-cheat system. Some of us were like, maybe we should have an AI that attempts to learn some kind of skill. Like there have been AI videos where AI learns to walk or it learns to like fly a plane or something. Uh, there are many like ideas thrown around, but we eventually decided to settle on this game because we all thought it'd be fun and we all like it. We all enjoy games. We have had not had we have not had much experience with Python, so it's kind of like learning on our feet kind of thing. We had to look up a lot of tutorials and stuff to kind of figure out how to best navigate Python. We we're also trying to figure out how to best integrate the agent, which would be like learning all the information we would be having after runs into the game and such. Like we had the game, uh, and we had to figure out how to integrate the AI. And while we were doing this, there were so many times when we would start the game and be like, "Oh wow, it runs, no more errors." But then, even though it would run, like you would hit spacebar and the game wouldn't start. It would just be like frozen there. Or I think there was this one bug where like the music would still play, but the game wouldn't play. It was just kind of stuck. It was just kind of frozen. There are other times where, like, the game, you hit spacebar, the game does start, but the character model would just be frozen in place. I think it was just spinning, frozen in place. And there's lots of other issues, but that's part of programming. We're able to charge our way through it. Uh, also, initially in the training, AI would misjudge the jump a lot. Um, I think Garrison was talking about it earlier, where like the AI got in a loop where it would be like constantly stuck. But we are able to get through that too. Some things we're gonna do next is like have the AI complete much harder levels. There are I think there's a level on Geometry Dash called Devil Max. It's a really hardcore level. Like top 10% of players are able to complete it, so that'd be really fun to do. I think what would also be pretty cool is that if the AI could like complete games faster, then it would be possible for a human to be like maybe if we had the game play at a frame rate that would be really hard for us as people to understand, but the AI would be able to eventually figure it out. That'd be cool. And since the AI has such an opportunity to play so many games so often, so long, it's possible that it will discover new tactics and new techniques that reinvent how we think to play Geometry Dash. It's happened before in other sports and other games, so it's possible that the AI discovers something we never really thought before. Redefine the game. So yeah, that'll all be fun things to do. Next slide.
So for most of our project, we worked together as a group, and we also tackled each task together. So in each of our group sessions, we would have one person share their screen, and they would be kind of the designated coder, while the rest of us would follow along and contribute by suggesting ideas, and we would also help debug if necessary. So we also had the following roles where we had Victor. He was designated to writing the paper, and he also created this PowerPoint. Whereas Garrison, Ben, and I were focusing on coding the program. And next slide.
That's it, I think.